নটে যোগ অনেক অনেক আমার অনার্স কম হয় তো কিন্তু সেকেন্ড টাইম করেন না তিন চারটে বেশি চালাচ্ছে ও পার কথা বাস করে দিয়ে ছিল অত বুঝি অত ঠাকুরের শুনতে পুলিশ ছিল আমাদের পড়াশোনা কোথায় গ্রাজুয়েশন কমপ্লিট আমি জায়গায় নামটাই মানসিক গুরুয়াটা মোড়ের কাছে এটা আমার ভাইকে তাহলে বাধা দিতে বলো না আমাকে আবার কিছু বলেন কলেজ যখন তৈরি তখন গভর্নমেন্ট রেট করেছে গভর্নমেন্ট থেকে আসতে গভর্নমেন্ট যদি কোনো 10 টাকাও দেয় তার ইনভলভমেন্ট অনেক বেশি হয় অটোনোমাস কথাটা ওই জন্য এসে দিতে তখন ম্যানেজমেন্ট বলতে আমাদের অটোনমি দরকার টাকা 10 টাকা দিলাম টাকা নেয় না চারটে কলেজ ছিল এখন মেডিকেলটা 1000 সিট ছিল তাহলে এসএসসি বাদ দিলাম 500 সিট ছিল আমাদের সময় তো ফাইভ ডিভিশনে পাস করলেও হাসিনার লোকে দাঁড়িয়ে দিত হাসিনে ফাইভ ডিভিশনে পাস করলে লোকে দাঁড়িয়ে দিতাম জয়েন্টে কাজ করতে দেখতে হতো এখন 98% এলো আমরা এগুলো দাঁড়িয়ে দিতাম ওই সময় ফাইভ ডিভিশনে পাস করলে আমাদের লোকে দাঁড়িয়ে দিত যেটা ফাইভ ডিভিশনে পাস করবে কোথায় 500 করে যেত আমাদের সময় ইংলিশ মিডিয়ামে 50-55 পেলে খুব ভালো চলেছিল এখন তো 99 পায় না আমরাও বাংলা মিডিয়ামে পড়ছি আমরা অসুবিধা বাড়ি বলতে মেদিনীপুর ঢাকা নিয়ে আমরা বাংলা মিডিয়ামে পড়াশোনা করছি তাহলে আমি ইংরেজি বলতে লিখতে করতে কিন্তু অসুবিধা হয় না কারণ টেন্স আর কনসেপ্ট শব্দ জানলে ইংরেজি বলা যাবে আমার টেন্সটা আমার সেটা ভালো না টেন্স আর কনসেপ্ট শব্দ লাগে একটা ভোকাবুলারি নেই কিন্তু আমি খালি ইংরেজি বলতে লিখতে করতে অসুবিধা হ্যাঁ ছাত্রী ধরে না আমাদের প্রফেসর এটা করলে তাদের ছাত্র আমরা হতে পারি আমাদের পড়াটাও তো হবেই না কারণ এটা ডিবেট করছে কোথাও বলেছি লাস্টে কাজ করে আমি কি হই হ্যাঁ ফোন করেছি না
Good morning, sir. Good day, sir.
খাই গেলাম হয়ে যাবে বুঝলেন তার মধ্যে। কতক্ষণ লাগবে তোমার? মিনিট 15-20 লাগবে।
Good afternoon to all of you. Myself, Dr. Joita Majumdar, Associate Professor of Department of Computer Science and Engineering. Welcome to our 1-week online faculty development program on methods for improving higher education, teaching quality using outcome-based education, pedagogical approaches, and NEP 2020. In short, OBENEP24 from 22nd July 2024 to 26th July 2024. Haldia Institute of Technology and Institute of Eye Care, Haldia, approved by AICTE affiliated to Macau, West Bengal, began its journey in the year 1996. It is the first private and accredited academic institution of technical education in West Bengal. The institute is situated at Haldia, an industrial hub in eastern India. Since inception, Haldia Institute of Technology is dedicated to the objectives of creating highly trained professional manpower in various disciplines of engineering, technology, and social science. The institute is also dedicated to the contribution of higher scientific research in technology as well as in applied science and social science. The faculty development program is organized by the Computer Science and Engineering Department of Haldia Institute of Technology. The Department of Computer Science of Engineering was established in the year 1996 with the vision to become a dynamic contributor to the community by ensuring excellence in academics and research in the field of computer science and to create an environment that will facilitate the growth of individuals in this field through innovative teaching, research with a strong tie-up with industry and society. The department offers a 4-year, 8-semester BTech degree course in computer science and engineering and 2-year, 4-semester MTech degree course in computer science and engineering. Students are motivated and trained up for GATE, GRE, TOEFL, CAT, etc. by our faculty members. The department is accredited Tier 1 by the National Board of Accreditation, NBA. Now, the objective of this FDP is to enhance the educational quality by aligning teaching methods with outcome-based education principles, National Education Policy NEP 2020, ensuring holistic development and improved learning outcomes. Now, the informal inauguration of our FDP by lighting the lamp and the Saraswati Bandana. Now, I would like to welcome our respected Principal Sir, Professor Subroto Mondol, on behalf of Department of Computer Science and Engineering, Haldia Institute of Technology, to inaugurate the one-week online faculty development program on methods for improving higher education teaching quality using outcome-based education, pedagogical approaches, and NEP 2020 OBENEP24 from 22nd July 2024 to 26 July 2024. Over to you, sir.
Thank you. Good afternoon, ladies and gentlemen, to this magnificently glorious day, the galaxy of such intellectuals and some honorable as well as my beloved students and other participants. It's a great pleasure to me that our computer engineering department is organizing a faculty development program on a basic topics which is required for these days because India is a developing country, so we always want to be a developed country. According to the sustainable development, we have prescribed 6 to 7 attributes where we can contribute for making ourselves from developing to developed country. And it is one of that is quality educations. The quality educations, it comes from NEP 2020. So we know more or less all knows about the NEP 2020. So the topics is nowadays that is outcome-based education. It is actually it is an educational theory that bases each part of an educational system around goals. Goals means outcomes. By the end of the educational experience, each student should have achieved the goal. There is no single specified style of teaching or assessment of OBE. Different teachers, different institute, and different classes, different types of outset the goals or outcomes. So outcome-based methods have been adapted in education system around the world in multiple levels. But definitely it has some benefits, clarity. So another is flexibility, another is comparison, much more. So I expect the number of speakers who are very much allied with these topics, they will give some highlights as all participants will give the benefits from this faculty development program. We always encourage to organize this type of faculty development program because that teachers always will be enriched or updated their knowledge as they can survive their teaching as well as they do not lose their style of teaching. So with these few words, and I wish a great success of this event. Thank you all. Joita.
Yes, sir.
Okay, please continue.
Okay, sir. Thank you, sir. Now, we'd like to welcome our respected Professor Torun Kanti Jana, Dean of School of Engineering, Computing and Informatics, and he is also the convener of IQSC Cell, Haldia Institute of Technology, Haldia, on behalf of Department of Computer Science and Engineering, to share his valuable thoughts regarding this FDP with us. Sir, please.
Okay, am I audible?
Yes, yes.
Yes, sir.
Okay, okay.
Yes, sir.
Okay, so good afternoon, ladies and gentlemen. Respected Principal Professor Subrata Mondal, distinguished resource persons, particularly found Professor C.R. Muthukrishnan for his significant advice and contribution, and he will be also delivering a speech on a very relevant topic, student-centric good teacher, organizer, program chair, organizing chair, guests, and all the faculty members. First, I would like to take this opportunity to convey my sincere regards and gratitude to all the members of the Computer Science and Engineering Department at HIT Haldia for organizing this wonderful FDP program spanning over 1 week and commencing from today. It will continue up to 26th of July. This particular department, if I can not wrong, that they have got a legacy of organizing this sort of workshop, faculty development programs almost every year, which I have witnessed for the last 4 or 5 years. mostly maybe in their domain, machine learning, artificial intelligence, and other related topics. But this time they have expanded the domain, which is really very generic one, which is very much attractive in the context of current days educational scenarios. And I believe that all the people, particularly the faculty who are participating in this particular event, will be extremely benefited for this undergoing this 1 week FDP programs. Coming back to the topic, there are three key areas. One is outcome based education, one is national education policy 2020, and the pedagogical approaches. These three topics are basically interrelated. For the sake of the audience, I would like to remind them that this computer science engineering department and HIT, along with three other UG programs, have recently been accredited by NBA in the last March 2024, and this accreditation will remain valid for the coming 3 years. So, but it does not imply that there is room for complacency. We have to move forward, we have to strive for excellence, and with this mindset, we have to continue, we have to channelize our effort to contribute significantly for further improvement. National education policy also include one of the major theme, that is the outcome based education. Dr. Joyita Majumdar Madam, during his inaugural talk, she was referring to the holistic approach. This holistic approach is extremely important in the industrial landscape, particularly for the young engineers, the students who after graduating of their 4 years BTech program, when they are about to join, quite often they fail to adapt in tune with the requirement of those industries. Usually we think about the knowledge and skills are the only requirement to emerge as a potential performer in an industrial scenario, but that is not the true case. That is not the sole requirement. There are a lot of other requirements, other qualities, other aspects are required, like cost parameter, working in a team, leadership quality, communication skill, respect to the values and ethics, environment. All these aspects are extremely important in an industrial scenarios.
Hello?
So whenever we consider the hello, please sir. Anyone? Okay. So proper blending of knowledge, skill, and other human faculties, when blended together, this can lead to the real holistic development, and which is extremely important for the industrial scenarios or for the professional organization. So keeping that in mind, this particular faculty development program, outcome based education, national education policy, these are very much interlinked with each other. And for your information, the day before yesterday, I was along with my principal was in Bhubaneswar to join one NAC workshop. NAC is another, that is another quality benchmark accreditation considering the entire institution as a whole. They are going for the sea change or the major reforms from the grading system to the binary system, either accredited or not accredited. There also we had witnessed that this outcome-based education, holistic approaches, pedagogical approaches is supposed to play a very crucial role in developing and grooming our students with the knowledge, skill, and the human faculties. Coming to the pedagogical approach, quite often don't take it otherwise for my self-criticism. We the teachers do have contribute significantly or put our endeavor while developing the syllabus, framing the syllabus, different modules, CO statements, CO-PO mapping, CO-PSO mapping, and of course the preparation of the lecture plan, how it will be developed. And pedagogy is basically how the lectures will be developed or how it will be the executed over the 6 months period, including its feedback and the corrective actions. But when the time comes for the execution, we become a little bit relaxed about the real implementation, how much students are learning, what are their lacuna, what are the shortcomings, and how to address those gaps. So this implies this pedagogical approach, whatever a particular teacher, according to his or her will, develop, it must be meticulously followed, it must be rigorously implemented, it has to be evaluated time to time, and the corrective measure, if at all, that has to be taken care of, so that after the completion of this 4 months period of syllabus delivery, along with the in between evaluation like unit test or the class test, viva, whatever it may be in the form, so that real value addition takes place. So that is the need of the pedagogical approach, which helps to attain the outcome in true spirit. So keeping all these things in mind, this outcome-based education, the pedagogical approaches, and the effect or the importance or the significance of this outcome-based education in the perspective of NEP 2020 is extremely beneficial and useful. So this faculty development program, which is being hosted by the Computer Science Department of Haldia Institute of Technology, is a wonderful initiative, I believe. And this particular time frame of execution, because this 2024-25 academic session is about to commence. So this is the high time to revamp our effort, our activities as regard to the syllabus, regard to the lecture plan modification or the development, how it will be executed, and keep a vigil throughout the 4 or 5 months, so that we can, or particularly the students can accrue the potential benefit of this outcome-based education system. So I believe that this particular FDP program will be immensely beneficial for all the faculty members and other participants. And also I would like to take this opportunity to convey my sincere regards to the different resource person who will be sharing their thoughts, their experience to enrich our faculty development programs. So thank you very much. With this, I conclude my speech. Thank you once again. Over to Joyita ma'am.
Thank you, sir, for your valuable thoughts. Now, with warm greetings, I would like to welcome our today's speaker, Professor C.R. Muthukrishnan, on behalf of Department of Computer Science and Engineering, Haldia Institute of Technology, and also thank to you that for accepting our invitation and delivering a lecture on student-centric good teacher. Here is the short description of our resume. Professor Muthukrishnan has been consulting advisor to CEO, TCS, Deputy Director and Director in Charge, IIT Madras, and Professor of Computer Science and Engineering at IIT Madras in his career spanning 40 years. He has guided 30 research scholars for PhD and MS degrees, over 300 students for MTech and BTech projects. Many of his students are holding top positions in academia and in reputed companies globally, and many as entrepreneurs have created startups and developed them successfully. He is actively engaged in accreditation work for NBA and NAC for about 9 years now. He consults for academic institution, industry in India and abroad, and is a mentor for many startups. He has served on many committees of MHRD, MEITY, DST, and DRDO. He was president of the Computer Society of India, a fellow and lifetime achievement awardee of the society. A chair in computational brain research has been established in 2016 at IIT Madras by K.S. Gopalakrishnan, his former student and co-founder of Infosys Limited. He is a BTech honors in 1965, President of India Prize winner for General Proficiency from IIT Madras, MTech and PhD in 1969 from IIT Kanpur. Now, welcome, sir, to our FDP. Sir,
Can I start now, please?
yes, sir, there is some felicitation from our department. This plant to you. Please accept it.
Thank you very much. I'm very delighted to accept. Looks
Okay,
beautiful.
sir.
Thank you very much. Yeah.
Thank you, sir, and over to you.
Yeah, thank you. I will open up my presentation to share on the screen and then I'll start talking. Please give me a minute.
Okay, sir.
Are you able to see the screen now, all of you?
Yes,
Yes,
sir.
sir.
Visible.
So, greetings and namaste first. I am really grateful to the organizers, the Department of Computer Science and the IQAC of the Haldia Institute of Technology for inviting me to participate in this FDP and the inaugural session and share some of my thoughts and ideas born out of experience, my experience for faculty and especially young faculty who are getting into the profession of teaching engineering in engineering curricula. The title of the FDP is Approaches for Quality Enhancement in Alignment with OBE, Pedagogy and NEP 2020, New Education Policy 2020. The slide should advance. Okay. The slide advancing.
Hello.
Yeah. I'm trying to move this slide 1 minute.
So can it be possible to make it full screen mode?
I think it's difficult because
Okay.
let me try. Okay. So this is the title of my talk, Student-Centric Good Teacher. I will share the entire presentation with the organizers.
Okay.
So you can have it for later reference for you. So I have chosen this title, Student-Centric Good Teacher. All of us want to be good in whatever we do. So we are all teachers, faculty in different departments of engineering, different programs of engineering. And so student-centric, that means our focus must be the student. The purpose of teaching is to add value to the student and make them equipped for a bright future when they graduate. That's our role. Once. So my sincere thanks to Mr. Umesh Pal, who has been communicating, corresponding with me, Dr. Jaita Majumdar, Dr. Momita Das, Dr. Rabindranath Sahu, Dr. Subhankar Jordar, and also your Dean IQAC, Chief Patron, Patrons and Advisory Committee, Haldia Institute of Technology. I looked at your website and I was able to see all the people connected with Haldia Institute of Technology. My presentation will possibly take me for about an hour and a half. It's 3 o'clock now. By about 4:15, 4:20, I should be able to complete 4:25. And if you have time, I'll be very happy to answer questions. I request you to put the questions on the chat box if there is one, so that they can be seen by the organizers and I can also see them and take it up. So our focus on 4-year engineering degree programs. We also have master's programs and PhD programs, where also teachers have a significant role to play. But our focus in this talk, I'll focus on 4-year engineering degree programs, particularly programs of a full-time nature where the student spends 4 years after higher secondary education +2 through a selection process and joins a 4-year program, 8 semesters, at the end of which he or she will qualify to get a degree and move on to a future, maybe a job, maybe a startup, or may go for higher studies, or may even take other opportunities like competitive exams and so on, or go for management, other disciplines and so on. So our students, though majority of them go for jobs, generally the 4-year degree program becomes a pathway to many options for them in the future. And the focus is on the 4-year program and the faculty who teach students in these programs. So these are engineering programs. Our focus on engineering. We have programs on pharmacy, architecture, many other disciplines. But my focus here will be on engineering. So we have many disciplines or branches in engineering: electrical engineering, electronics and communication, mechanical engineering, computer science and engineering. And there are also many new avatars now. There's a program in AI and ML, AI and data science, cyber security, and so on. So what do students generally expect? Of course, the students join this program depending on the competition. Generally, the choice will be like flies on a sugar cube. All or many students want only a few branches, but however, eventually they take what is available to them through some process, through some procedure, and take up that program. And after 8 semesters, they successfully complete the program and get the degree. So what do they expect? Most of them expect a placement, something to start with. It's not as though the placement is only a job, but generally it's a starting point for a career, for a profession. So many of them over 5 years, 10 years and so on will change, will go into many new things and so on. But initially it's a placement. And this placement generally meets industry requirements, okay? Because the industries who are able to offer. Of course, there's a wide variety of industries, including public sector, private sector, government, small scale, medium, large scale, and so on. And sometimes students also select and go for opportunities in other countries. What do students ask a teacher in any course? Sir, will this come in the exam? That's what they ask, because they all want to focus on exam and do well in the exams and thereby earn the credits for the degree, fulfill the requirements for the degree. So the student focus on clearing exams, doing well in the exams. That's the focus. So what is engineering? We can take a traditional view and say it's a body of knowledge. There are many branches of engineering: electrical engineering, mechanical engineering, chemical engineering, civil engineering, and so many branches. You can say it's a body of knowledge, but coherent knowledge, so that in a certain field, the person will be equipped or prepared to take up various types of jobs. Maybe a design may involve production, may involve troubleshooting and maintenance, all kinds of different types of work, and so on. Who is an engineer? And so, see, the traditional view does not carry too far, because now we feel many fields are converging in some way. For example, those who study mechanical engineering or electrical engineering, for example, they may have to go and look at electric vehicles and so on. So quite a bit of electrical engineering knowledge is required. Also, mechanical engineering knowledge is required. So the body of knowledge view sometimes become a very tight water compartment. Apart from, so you ask the question, who is an engineer? Engineer should be able to solve problems. First of all, identify and uh, and catch the right issue in the problem. Because you may produce a good solution, but if it's not for the problem required, it's not going to meet any purpose. So solve problems, which will include design, analyzing systems, diagnose and troubleshoot, and fix problems and so on. Of course, these different activities may generally be in a certain broad domain, like electrical engineering, but within that also we have specialization like machines, generators, transmission, distribution, and so on. Similarly, if you take mechanical, you have production, you have design, you have CAD/CAM, you have thermal, so many different subfields within that. In addition to doing the above, an engineer should also work in a team with other people. No one engineer solve or produces a solution all by himself. He has to work as part of a system with other people and so on, team. He or she must be able to use tools. Every engineer will use some tools in their work. When I studied engineering, I used slide rule and logarithmic tables, and then calculators. These are the only tools available now. Now, there are very many more sophisticated tools are available. For example, I can mention MATLAB or for circuit design, for VLSI design, for stress analysis. So many different tools are available. And communicate with, again, members of the team, and also keep abreast of developments in the field. At the end of 4 years, when the student gets the degree, he has some preparation, but as he goes along, he has to keep learning on the job, and he also may have to learn new things and so on as they go along. So these above requirements for engineering can be captured in terms of what we call attributes or professional competencies. We use the word competency. See, the word knowledge and competency are different. Competency is about being able to use the knowledge for some specific requirement for some purpose. Whereas knowledge by itself is, knowledge can be in a library, in a memory stick, or it can be in a book and so on. But only when it is applied, right? So competency is the word. So on a graduation, a student has to possess these competencies. So this is the basic idea, and it pervades all engineering disciplines. So I understand that at Haldia Institute of Technology, you already have got accreditation from NBA, so you may be familiar with this, but I'll very quickly mention them. These are called program outcomes. So program outcomes specify what an engineer at the time of graduation must be able to possess as competency. So apply knowledge. What knowledge? Knowledge of mathematics, science, engineering fundamentals, and an engineering specialization to the solution of complex engineering problems. Similarly, analyze complex engineering problems to reach conclusions using mathematics, natural science, and engineering sciences, and so on. Do design. Sometimes the design may be ab initio, sometimes it might be an improvement to your existing design. Then investigate complex problems, troubleshoot, or pain points will be there in certain systems. There may be failures and so on. So how to analyze the situation, how to troubleshoot and so on, and come up with solutions. Sometimes we may want to do this investigation not because there's actual failure in a system, but we may simulate a failure. For example, in automobile engineering, how the vehicle will behave in the case of a crash or accident is tested before. So this crash testing is part of the final acceptance of an automobile by regulatory authorities before it can be made available to the public. Similarly for airplanes and so on. I'm just giving some examples, right? So this investigation may also be part of a test to approve a product. It need not necessarily be only in the field. Tool usage I already mentioned. So these are the 5 important attributes. We also have another 7 more, which I'll very quickly mention. So this is engineer and society. Your Dean IQAC also mentioned this in his talk to us. Environment and sustainability, ethics, individual teamwork, communication. Communication includes being able to present one's work also. Not necessarily in the form of, it may include notations, diagrams, and visualizing data and so on. Project management and finance, lifelong learning. So these 12 are called the program outcomes or attributes, graduate attributes. So this is the basis of how we want to look at our job. So as a teacher in a course, my work for the students in front of me in that subject in a semester is to equip them in these requirements or in these 12 requirements, but not completely, because the entire curriculum is what will achieve that. I'm only doing part of the curriculum. So this brings out the point that as a teacher, if I'm teaching one course, I should also have some broad perspective of the entire curriculum in which this course is fitting, right? What have students done before they came to my course? What will students do after they successfully complete my course? These perspectives are important for a teacher. If I draw rigid boundaries about what I am teaching, then I am not connecting the students with respect to what they learned before and what they are going to learn afterwards, all of which taken together is what will help the students to realize these program outcomes. That's a very important point to keep in mind. Connectivity. The entire curriculum is connected from the point of view of the student and his being able to achieve the program outcomes. Okay, so next we ask the question, how are these program outcomes attained by students? They achieve these program outcomes through curriculum, co-curricular and extracurricular activities. It's a total experience. It is not only the curriculum. We must keep that in mind. Though, of course, as teachers, we pay attention only to the curricular aspects mainly. Sometimes, to some extent, also the co-curricular. But extracurricular activities, which are also important, especially for a teenager who's come from school to do a 4-year engineering program, they will be taken care of by other parts of our institution. There will be a dean of students, there will be hostel wardens and so on, and students will have cultural festival, technical cultural festivals, so many other activities, clubs and so on. So all of that will figure. It's a total experience. Why should we keep this in mind? Because the student time has to be apportioned for all these activities. As a teacher, I should not think the student's time is completely mine and mine alone. If 4 or 5 teachers in a semester think for the same section of 60 students, let us say, if each one of them think the student's entire time for the entire semester is completely mine, then how will he or she engage in other activities? So we must keep this in mind and optimally use student time as a teacher in the course to help him progress in realizing the program outcomes. So we'll focus on curriculum. We will not say much about, there's a curriculum design, there's a structure for a curriculum, there'll be syllabus, and there'll also be study materials. So this is already designed. In this talk, I'm not going to focus on how we do this, all these things. But when we come to NEP, we'll see that there are some recommendations which talk about how the curriculum should be broadly organized. So this is important. When I am a teacher in a course and I'm looking at the course, I should also know the entire curriculum. What are the core courses of the curriculum? What are the core courses that the student has already completed before taking my course? My course will be a prerequisite for what courses to follow in the curriculum. So this must be understood by the teacher. It's a connected uh, input that goes with. So how do we implement the curriculum? Teaching, learning, and assessment. TLA, teacher. So there's a classroom or laboratory, some teaching takes place. It could also be a project with guidance. It could be a industry internship. Student could do a MOOC course. Many curriculum now permit students to take a MOOC course in place of an elective, not one, maybe even 2 or 3 MOOC courses like SWAYAM or NPTEL, so that they have exposure to a different cohort of students with whom they can compete. They can also experience something other outside their own institution, and more importantly, they can pick up the threads of how to learn by themselves in future, because they might be able to use e-content available later on. Then, so this teaching learning assessment must be constructively aligned. The word constructive alignment is very important. Constructively aligned means what I teach is what the students should be learning about, and what they learn is what should be assessed. Okay, there must be a strong, good connection. So this is a broad general picture. Now we'll go to the. Okay, so now we'll look at outcome and some examples of that. Yeah. So course outcome, I will only talk about course outcome. Program outcome we have seen briefly. And I'm sure you will have other sessions in your FDP where this will be gone into in detail. I've noticed that in your FDP you have professors from Jadavpur University, ISI, and also NITTTR Kolkata from outside. So I'm sure those sessions will touch upon more details in a complete fashion. So course outcomes state what a student, on successfully completing the course and earning a pass grade and getting the credit, can do or demonstrate, can perform, can do. So it's not just knowing, it's something about what to do with what he knows at the end of the course. So these are referred to as learning outcomes or student outcomes, but NBA uses the term course outcome. In other systems which are followed, they use words like learning outcome or student outcome, but we use the term course outcome. But whatever it is student centric. It is not the course, but it is what enables the student at the end of the course. What the student is enabled for is what is talked about. Okay. So sometimes we use the word competence, sometimes we also use skills. Okay. Now we'll see a few examples of course outcomes, very important. So if you're teaching a course in a curriculum as a teacher, you should look at the course outcomes very carefully and try to grasp the essence of what the course outcome wants the student to be at the end of the course, and connect the curriculum description, the syllabus, and the study materials to the teaching of that course, and thereby the learning and the assessment in the course. That's called constructive alignment. So constructive alignment has course outcomes, curriculum, then it has the teaching, learning, and assessment, all those components. So I'm now going to look at some examples of course outcomes. This is a course on Engineering Mathematics 1. I've not referred to any particular curriculum here. I've taken a general curriculum, and I've taken some common courses which are given to students of engineering in mathematics, physics, chemistry, workshop, and so on. Some simple examples I've taken. So this is a course on engineering mathematics. There's an important question here. Should all branches of engineering students learn the same topics of mathematics? Is a vast subject. It's a very big subject that's developed over several centuries. We also have traditional mathematics, particularly in India, we have in our country. So we cannot teach all of mathematics in one course or even two courses. So what should students learn in a course in mathematics for engineering? Should it be specific to engineering? Should it be general? Or some of it should be general, some of it should be specific to the engineering branch? Earlier, most of the engineering branches were centered around energy, electrical energy, mechanical energy, chemical reactions, and so on. But now, quite a few branches of engineering are centered around information, data, information, how to process information, so on. These are not disjoint. Energy and information are not disconnected. They are connected, but the focus is on information. For example, in computer science and engineering, the focus on information processing. We even have courses titled Information Technology or Computer Applications and so on. Whereas in mechanical engineering, chemical engineering, electrical engineering, the focus is on energy, all right? How to use energy to move materials or to remove heat or to add heat and so on, various processes. So the question I'm posing to you is that should the common course in mathematics be identical for all engineering, or can they be differentiated to some extent? Not 100% maybe, but to some extent. Keeping that in view, let us look at the course outcome. Solve first order ordinary differential equations using methods to calculate integrals. So first order ordinary differential equation, you will finally get an integral on the right hand side if you adjust the equation and bring everything to the right side. So how to calculate integrals? You may say they have learned this in school. Many of them would have learned in school. But even then, it is worth spending 1, 2, or 3 lectures on this in a course on mathematics. Typically, a semester course has about 40 lectures, maybe sometimes 45, 15 weeks, sometimes maybe 36, 12 weeks or 13 weeks, if it is 3 lectures per week, whatever it is, and tutorial. So this is sort of connect. You see, they might have learned it in school, but we should still provide some kind of a bridge to draw them from school into the program. Course outcome 2, model physical processes, examples, Newton's law of cooling, electrical circuit, rectilinear motion, mass spring system, using mathematics, ordinary linear differential equations. So even though there's a course on mathematics, we should view it as an engineering mathematics, applied mathematics. So we should talk about how certain simple engineering system, like simple pendulum, motion, harmonic motion, or a simple electrical circuit like just a resistance and a capacitance, or a battery. How do we charge a battery? Right? We connect it to a source, some simple circuit. So take those and formulate the parameters of that as a linear differential equation, ordinary linear differential equation, and then proceed. So that modeling part is important. You might devote about 6, 7 lectures for this. So it's important to do this right in the beginning so that the motivation is strong. Students don't have to wait for an answer why they are learning this for next semester or for 2 semesters later. They will get it right then and there that I'm learning this because these simple situations in engineering connect with what I'm learning. Third one, trace the curve for a given equation and measure arc length of various curves. So this is very important. Most of the mathematics that we teach in engineering courses today, they do it symbolically. Everything is symbols and so on. But actually, for an engineer, these symbols have to be converted to diagrams and plots and so on. Right? That's very important. It must be part of the mathematics course. So give them a graph sheet, ask them to plot a curve and so on. Simple solid geometry using equations of sphere, cone, cylinder with problems. Right? So these are 3-dimensional objects. Evaluate multiple integrals and apply to find area bounded by curves, volume bounded by surfaces, center of gravity, and moment of inertia. So look at this entire course. This is very different from what we are now teaching in, let's say, first year course in mathematics. We go into a lot of detailed topics of mathematics, which is good. But the point is that is the connection with engineering happens in that course or does it happen later? So I prefer these kind of outcomes to be written for a mathematics course. Of course, you can write whatever outcomes you want, but ultimately those outcomes should help you as a teacher and give you the constructive alignment of teaching, learning, and assignment. That's important. Let me look at another example. I have lots of examples. I'm not going to go through all of them. I'll look at a few of them here. This is engineering mathematics 2. Let me show this one. I'll quickly run through more of them. Yeah. Fourier series representing harmonic analysis of periodic continuous systems. Okay. In fact, if you use a tool like Mathematica, for many of these, you can give a problem in the mathematics. See, instead of doing only analytical symbolic mathematics, do symbolic mathematics like, let us say, Fourier series representation for some simple function, but ask them to also see it in the Mathematica with actual numbers. All right. Because engineering is not about only symbolic mathematics, it's about using mathematics. In other words, what we should attempt in the course is not help students learn how to do mathematics. We should help them to learn how to do mathematics and use mathematics. Both are important. Okay, so I will move, I'll quickly run through for want of time. So this is a course on engineering physics. Typically we teach in the first year. Again, a question to ask. Physics, mathematics, chemistry are very vast subjects. You know, people study them for something like 7, 8 years, 9 years, and so on. And some of them also become good engineers. For example, all our nuclear program and space programs in our country may have basically science, advanced science postgraduates and graduates and so on, who might actually be doing good amount of engineering. Similarly, engineers also can do that. So what do we teach in physics? Should it be common for all branches? Can it be differentiated? To some extent. I'm showing one sample here. Interference, diffraction, polarization, and the application engineering. We know interference, we know diffraction, we know polarization. This is basically you take some part of the spectrum, visible part of the spectrum, and conduct some experiments and show that you get patterns and so on, or the rays will change directions and so on. But you have to also talk about where they're used in engineering. Very important. Lasers, optical fibers, and how used in some industrial applications. Theory of semiconductors and the application in some semiconductor devices. Basics of magnetism and superconductivity, the applications in engineering. Nanomaterials and their application. Note that this may be a very heavy course. You may not be able to do so much. I've given 5 outcomes. Sorry, this should be CO5. I'm sorry, I numbered them wrongly. CO1, CO2, 3, 4, and 5. 5 applications. If you devote approximately 9 lectures for each, this is a heavy course. You may want to do only 4 of them. Drop one of them or keep one of them as an additional topic, depending on the time permitting and so on. Okay. Look at them as samples to draw upon and ask yourself whether your curriculum is well designed in this respect, at least with respect to the overall structure and the course outcomes to be specified for each of the courses. This one is on engineering chemistry. You can go through this. For example, CO5. On completing the course, the learner will be able to identify chemical compounds based on their structure. All right. On completing the course, learner will be able to explain causes of corrosion and methods of minimizing corrosion. So basically, you can't teach very much, but what you can teach in the time, student time particularly. Remember, curricular, co-curricular, extracurricular. So don't overload the student. If we eat too much, we don't digest anything. Very important to remember. So keeping that in mind, these outcomes have to be properly drawn and used. This is a very important aspect of pedagogy. Unless you have your outcomes set right, your pedagogy is not going to help the student, not only in that course, but also in the overall curriculum in terms of achieving program outcomes. I will leave this for you to study. Similarly, basic electrical engineering. We feel that irrespective of the branch of engineering, for all branches of engineering, some basics of electrical, basics of mechanical is required. All right. Maybe also basics of civil. But we can't again expand this too much. So it's a challenge to find what is a common for different disciplines of engineering and bring that into the common curriculum, common core curriculum. So here I put difference between electrical and magnetic circuits, then apply and analyze the resistive circuits using star delta conversion, etc., and so on. This might be a little heavy for the first course, but I leave it at that. You please study that. Okay. And this is a course outcome on basics of electronics engineering. Explain the working of PN junction. See, again, this is becoming important because even so-called core branches like mechanical engineering has now created additional discipline like mechatronics and so on. Aeronautical engineers, their specialization in avionics. Many of the automobiles have quite a bit of electronics in them. All right. No modern car or modern vehicle can be useful and can serve can meet the needs adequately without reasonable amount of electronics. In fact, and so on in it. So select sensors for specific applications. So normally, we put selection of sensors very late in the curriculum. So many of these courses may have to be also go with an attached laboratory. Very important. So that students get some idea of different types of sensors, how they work, and so on. There's 6 outcomes. It might be difficult to capture all the 6 in a 40 lecture course associated with, let's say, a laboratory and so on. But you can optimize it. But this is a kind of framework thinking that we should have for looking at common engineering program. Okay. This will be the last one, engineering graphics. Normally we have a course on graphics and workshop in the first year, common course for all students. I think it's a good idea because, some amount of graphics help visualization and so on. So draw fundamental engineering objects using basic principles and rules. How to draw clearly, a cone, a circle, a sphere, and so on. They may do some of this in the school level, but it's worth. For a CO like that, you may not devote 9 periods. You may not give equal weightage. You may do it just in about, say, 3 or 4 classes, okay? But give some problems, some exercises. Construct various engineering curves using drawing instruments, okay? So the first 2 are actually connecting geometry with diagrams, with precise measurements and so on. Apply the concept of orthographic projection and so on. Draw fully dimensioned. I notice one thing. Many of us who become faculty in engineering, we have gone through the curriculum ourselves earlier in getting our BE degree and MTech degree and so on. But we are not able to connect those courses which our students are now doing. You don't have to be a teacher of engineering graphics, but you must have some appreciation of what this course is about. So that if you're later teaching, say, for example, a computer graphics course, you can draw upon something that students have learned in this course, in the later course. This connection is very important. The student's learning is actually in connecting the dots. The dots will only give you a feel of a pattern. The actual full thing emerges only when the dots are connected. And connecting the dots cannot be left only to the students by themselves. It has to be induced by the teacher, both when you put the first dot and later when you put the other dot which are going to get connected. So this connection is very important. When I teach a course to my students, I should remember what they have learned before and how I can connect what I'm teaching. And I should also keep track of what students will learn later, to which my course is going to be a base or prerequisite. All right. On last one on workshops, I think. This is engineering chemistry, programming and problem solving. I'll skip that. Engineering mechanics, I'll skip that. Workshop practice. Yeah, this one I'll show you. There are several. So workshop practice, what are the outcomes we state? Familiarize with safety norms. Any workshop, the person has to be safe, very important. Remember in the PO also we showed some aspects of these. Handle appropriate hand tool, cutting tool, machine tools to fabricate a job. How to handle tools, how do you pick it up, where do you leave it, and so on. These are these may not be a very deep knowledge, but they're very important because indirectly students learn many things in this. How they should later, if they have to be in a shop floor, how should they handle their responsibility in the shop floor and so on. Understand the construction, working and functions of machine tools and their parts. Know simple operations, turning, facing on a central lathe. You may do these outcomes through some samples, some pieces to be actually fabricated to specify dimension in the workshop using different machines. Maybe a drilling machine, maybe a lathe, or maybe a depends, if it's a carpentry workshop, they'll work with wood, otherwise they may work with metal and so on. But you need to have this kind of, so you see these outcomes make it clear to the teacher and the taught, both, and the system, what is being done in this course that connects up with the whole, the big picture, right? That's very important. So I will not take up more examples. I have a lot more examples. I will skip them. Basic electronic engineering and so on. Problem solving, mechanics. Project-based learning. This one I will show you. So in many curriculums, students do projects. Sometimes they may do it as a final year project, what we call capstone project. Sometimes they may do it as part of a course. Sometimes they do it as a mini project. Sometimes they may do it as a minor project in the course. Sometimes the course may include project as one of the components. Okay, this is very important. Project-based learning is very important. In addition, students also do project type of activity when they participate in hackathons, design thons, and various those types of technical events. So it's very important. So what is identify real life problems by exploring sources, focus on societal need. That's the first outcome. So a problem must be culled out, identified by exploration, right? By observation. Where is the pain point in for somebody in doing something, right? In using a tool or whatever it is, or in repairing a machine. So identify a problem. So sometimes you so that it can be taken up for carrying out further project activity. Analyze the identified problem in technology perspective. Very important. In engineering, we want to produce engineering solutions. I don't want to recommend solutions like, you go to a soothsayer or a psychologist or something like that. Right? So this must be technology-based solutions. Propose suitable solution using knowledge. So typically, project-based learning can come maybe in the fourth semester, because by that time they would have learned some basics. But some curricula include project-based learning in the very first semester itself. I've seen in our country, I'm not talking about countries elsewhere, there's something called a tinkering lab. So they may not have the knowledge, but then as part of doing a project, they learn some things. So the project activity, which is highly practical oriented, what is required to be learned will be learned. And typically the first year projects that I'm talking about are done by a small group of students, like 3 or 4 students. And these students the groups are formed across disciplines. It's not within the discipline of mechanical. There may be one mechanical, one electrical, and maybe one civil engineer, some 3-4 people together. Of course, to do this, you have to give them the problems. They will not have sufficient time to do CO1, explore and identify the problem. So we have to create the problem, and a lot of sources are available. For example, if you scan learning materials of other universities, e-courses, and so on, many such sources are available to spot such problems. Of course, we may have to connect it with our local needs in some way. So inculcate the attitude of individual and teamwork for lifelong learning. Demonstrate solution present in written oral form. So the project should culminate in a demonstration of the solution, which will be presented both in written form and also communicated with words. A presentation, something like that. Okay, I'm going to skip the rest of this. Let me go to, So there are more examples. You can look at them later, but I can't overemphasize the importance of having good COs and not making them too heavy, not making them too light, so that a course, along with 3-4 other courses for a student in a semester, makes judicious use of student time for the teaching, learning, and assessment activity. So writing COs. I'll be later mentioning what is called Bloom's taxonomy in the next few slides. It's very important to keep in writing COs, course outcomes. First of all, course outcomes, every course outcome should have a verb in it. Some activity, something to do, something to demonstrate, something to calculate, something to design, something to solve, something to analyze, something to troubleshoot, like that. It cannot be impart knowledge. It cannot be, student will know this and so on. Because that is not, that description does not give you a way to assess or test whether a student has achieved it or not. Suppose I say students should have knowledge of electrical circuits, RLC circuits, or students should have knowledge of flip-flops, different types of flip-flop circuits. How do you test it? It's not exactly, So course outcomes must be written in a fashion so that, I told you earlier that student will ask you, sir, what will come in the exam? All you have to tell him, look, what will come in the exam is what the COs describe. That's it. Okay. So let's go back to Bloom's taxonomy. We have these 6 levels. I won't go into the history of Bloom's taxonomy, but it's very useful to understand. So, as I said here, Bloom's taxonomy is widely used in education to take students beyond simple memorization. Rote learning or memorization is only a starting point. It is not that it is not important. Some amount of memorization is important, but memorization alone is not sufficient to achieve professional competency. Okay, what is memorized must be, student must be able to make use of it, apply it, make use of it, and so on. So Bloom's taxonomy talks about these 6 levels very quickly. I'll mention: knowledge, comprehension, application, analysis, evaluation, synthesis. Okay, you can. These levels are important because they give you some kind of a progression in the depth of learning of a particular idea. All right. So the levels 4, 5, and 6, 5 and 6 particularly, are very high or advanced levels. And levels 1 to 4 are somewhat basic levels, starting with level 1, 2, then 3 and 4, and so on. They go in that order. So Bloom's taxonomy itself is again in cognitive, affective, and psychomotor domains. Let's not worry about it. I'll only take cognitive domain here, which is by and large connects with, or by and large is applicable to engineering degree programs. But if you take an engineering technician program like Polytechnic or something like that, maybe psychomotor domain will also help, right? Or affective domain is about intelligence, emotional intelligence, and so on, response and things like that. That may apply, for example, in a law degree much more. All right. So all the three domains are there. In fact, all the three domains are important for all professions. However, the focus will be much larger in cognitive domain in a 4-year engineering program and compared to the others. So we'll focus on that. Okay, this slide is very important. It will be available to you. I'll quickly project it. There are two references which are both available. You can download them. They're very good references to read. They're slightly outdated. They were published in 2018, end of 2018 by ASCTE. One is on examination reform policy. Other one is model question paper for undergraduate programs for several disciplines, particularly the traditional disciplines. Full 3-hour exam papers are given, and each of the papers pertaining to a subject, the COs of that subject are given. So you should read the CO and then the question and see how the questions and the COs have a strong relationship with each other. So I will leave them as references for you to study. I'm not, you won't have time to go into them in any great detail here. Okay. Yeah. So we use the word complex problems, right? In the PO1, if you recollect, first 5 POs use mathematics and sciences to solve complex problems, then analyze complex problems, design complex problems, troubleshoot complex problems, use tools to analyze, design, whatever it is, for use of tools for complex problems. So what is complexity? There are many, you can say real life. Complexity can come in a variety of ways, but I'm giving only some idea here. Simple to complex is not a binary. It's not that something is simple or complex. Okay, that it's a spectrum. It's a continuum. There are many. So we can progress from simple to complexity in many stages. Non-linearity is one of the important complexity issues. See, if you look at our curriculum, our focus is so heavily on linear systems. I've analyzed some curriculum as part of my own interest in study, and also as part of some groups asking me for help and so on. And I found the curriculum is a very, very high percentage is concentrated on linear systems. For example, in control systems, in PID control, in chemical engineering, so many places we focus so much on linear systems, but non-linear systems are also important in practice. For example, many of the digital systems today use switches. Switches are basically non-linear, right? Static equilibrium, dynamic equilibrium, then transients, size and scale. Complexity of a system can come from size and scale. For example, if I have to design a circuit with something, let's say, few thousand elements, it's it's complex enough. But if I have to design with several million components, it's much more complex, right? So that's another thing, and so on. Then reliability, fault tolerance, and so on. What happens when a system fails? How do we diagnose a failure? How do we bring the system back to life? Do we repair online, or do we have a standby? What kind of a configuration, and so on? Then use context. Who is the user? What is the user interface like? For example, in mobile phones and personal devices, medical instrumentation, so on, it's very important that the interface is something that is very convenient. It will not be prone to inadvertent misuse by the user by mistake, because it can create a serious consequence, right? And so on. So the idea in this is that the essence of this complexity is captured in what is called higher order thinking skills, HOTS, higher order thinking skills. This is very highly valued by industry. All right. Of course, some industries may ask for very specific requirement. That's a different thing. But across many industries, they want engineers to solve problems and that problem solving will require higher order thinking skills to some degree, to some extent. All right. Some of it may be acquired on the job with experience and so on, working in teams, but a preparation must happen in the 4-year curriculum. And this higher order thinking skill is what is captured by Bloom's taxonomy. Remember those levels, remembering, comprehension, analysis, and so on. Okay. So that's the connection between complexity, Bloom's taxonomy, and course outcomes. Now we'll move on. Okay, this shows the Bloom's taxonomy in a diagram form. It shows in a diagram form, remembering, understanding, applying, analyzing, evaluating, creating, or synthesis. Okay, so you may want to bring the highest level in terms of some innovation, for example. All right, participating in a hackathon, some design thons and things like that, technical competitions and so on. Evaluating, they should be able to analyze different alternatives and be able to give the pros and cons for the different alternatives and so on. Okay, and so on. So Bloom's taxonomy is hierarchical, meaning that learning at the higher level requires some skill to be at the lower level to be obtained. So you cannot bypass, you cannot directly jump to analyzing level. You have to build up from remembering, understanding, and so on. For example, if you take electrical circuit, Ohm's law may have to be remembered, or the voltage across the capacitance is 1 by C integral I dt, integral of I with respect to time. That's how a capacitance stores energy as a charge. So these may have to be remembered. If you take integration mathematics, some integration by forms have to be remembered. You may not work everything from first principles, right? For example, integral of x to the power n dx is x to the power n plus 1 by n, or n plus 1, whatever it is, that's all. Then you can go to integration by parts and things like that. So that's Bloom's taxonomy. Okay, these slides I'll go through very quickly. How do we use Bloom's taxonomy? Well, Bloom's taxonomy is captured by what type of questions in examination or in Viva will correspond to a Bloom's level. The key in the question is a verb. What are you asking the student to do? All right. So let me move a little bit quickly. So these are the Bloom's verbs it shows. These are the different levels, low order to high order, from as you see the screen from your left to right, and then from top to bottom are the various verbs that are applicable in that order. Remember, you can say describe, name, find, list, define, and so on. Examine, explain, compare, explain in your own words, okay? Not explained by reproducing. Compare, discuss, and so on. Apply, complete, use, examine, analyze, and so on. So these are called, you can study them in detail. There are more examples that are there in my presentation. So these Bloom's verbs are important because they guide you how to design questions from a CO. Given a CO, which I have taught in the class, I have to give students practice problems. I also have to give them homework or assignments, and also have to give them exam problems, right? Internal exam, end semester exam, whatever it is. So for that, this guide will be helpful. Okay, this slide is very important. What this says is that the first 3 levels, and to some extent the 4th level of Bloom's taxonomy, can be assessed by written examinations, right? Because written examinations, you have MCQs, you have diagrams, you have solved problems, you have patterns for a written exam. But it could also be an open book exam sometimes, doesn't matter. But the higher levels of Bloom's taxonomy, particularly evaluation, creation, and so on, can be assessed only through course projects, mini project, minor project, or capstone project. They require some activity, some task to be completed by the student, based on which you will do the assessment. Okay. So if you look at the curriculum, maybe the courses in the later semester, maybe from the 5th onwards, may include more components of the higher type. Not exclusively, they might have some of this plus some of that. So don't look at it as a binary again, but these are, because that's why analyzing sort of combines both. Okay. So as a teacher, we may have to also engage our students in some courses for these type of activities, some small projects and things like that. Okay, now one more example of course outcome. I've given one more example of course outcomes here. I've taken it from, this is generally applicable to mechanical engineering, chemical engineering, to some extent also maybe electrical engineering. Course on heat and mass transfer. Typically, these are taught as two separate courses. Sometimes they are combined into one course depending on how the curriculum. For example, for biotechnology students, you may do it as a single course because many of the biotechnology processes involve both heat and mass transfer. You may not do it as two separate courses, but mechanically you may do it as two separate courses. So I've put 7 outcomes here. They're a little heavy for a semester course, but look at each outcome: solve, evaluate, analyze, design, analyze, determine, perform, and so on. So very important. So again, I've taken this example later because this pertains to engineering. Earlier examples are all physics, chemistry, mathematics, and engineering courses in the first year, the beginning part of the curriculum. These will be in a core curriculum, let us say. Core, typically the curriculum has a common core, engineering core. It has a professional core, it has professional electives, then it has open electives and so on, many other components, right? So this may be part of a professional core for certain disciplines. What I showed earlier could be part of the common core for many disciplines, for all disciplines or many disciplines. So that's why I put this example in this place. Okay, these slides, I'll just expose them very briefly. So remember I showed you verbs for Bloom's taxonomy for different levels. So these actually gives more details about that. For example, remember level, the question cues or verbs will be list, define, describe, recite, etc., identify, label, tabulate, and so on. So the same material but in a more detail. I've taken these slides from the 2 references I gave you earlier. They're all there in that reference, okay? So this shows similarly for the other levels, what are the cues. So it can just continue. The same material, it covers all the different Bloom's levels. I will not look at all of them. For example, evaluate level, what is the skill that is demonstrated? What is the competence? Compare and discriminate between ideas or solutions for ideas. Assess values, and so on, so on. Please use it as a study material. I won't be able to go through them completely here. I'll skip these. Yeah. This I'll show. These are sample questions for level 1 or remember level. State Ohm's law. List the physical and chemical properties of silicon. You just have to remember them. Some basic things have to be remembered, and it's at least it's important enough up to the point of the examination. Maybe much later, the student may not actually memorize it. He might use a reference table, or you might use Google or something and find out. That's okay. But during the process of learning, getting everything from outside is not okay. Some of it must see. Learning actually is an activity where we develop our brain, our intellectual ability, cognitive ability to assimilate something. Maybe it will evaporate over time. That doesn't matter. But at least for that course and maybe also subsequent courses, this may be important. For example, an electrical engineering student must be able to state Ohm's law anytime after he has joined the course, maybe after the first semester, right? He can't say, I learned it in the first semester, so I don't know it in the third semester. Not acceptable. And so on, so on. I'll show you a few more examples. Yeah. So these are questions for the apply level. Look at the questions. Turning on, off. Turning on of a burger alarm only during night time when the locker door is opened. Okay. So you remove the lockers have a door, and normally you use a code to open it. Right. If you use the wrong code, it will not open. And in that case, it might be an attempt by somebody to it may be attempted theft. So you want to sound an alarm. So the problem is a sound alarm must be turned on if it is night time when the door is attempted to open, but there's a failure. The code or key is not the right one. Let us. So there is a misapplication of the key. It's night time, and you want the burger alarm to be served. So what will the student do for this question? Well, there are several things he can. The question is not complete. All right. So he might, for example, just give the logic. All right. So, for example, how to detect nighttime? Maybe there's a clock in the system, and the clock reading will be used or something like that. So he can only give a schematic of the solution, and later he can implement it and so on. All right. This is an application, very simple application. So we have to give problems like this. So that's the purpose of this example. For different levels, what kind of problems can be given? I will show this one. See, these are some sample problem need statement. They'll come at a higher level, okay, in the Bloom's taxonomy. For example, let us look at the three. Biotech industry needs automation for filling its product into 20-liter bottles. Design a system to meter the flow into the bottle so that each bottle has 20 liters of liquid. So the bottle will come into a station, then the flow will be activated, something will fill in the bottle. Exactly when 20 liters is filled, you have to cut off the flow. All right. There'll be more than one filling station. The system has to monitor all the filling stations as well as keep count of the total production on a daily basis. So so these are system problems, right? So you have to first draw a block diagram of the system. What are the inputs and what is the logic needed to implement it? So this will use a lot of knowledge from different courses plus some additional learning. So you can view this as some kind of similarly. There are many problems in that. You can look through that. Okay. Yeah. Okay. What this before this there was a question paper of a 3-hour exam. What this shows is that each question is marked with which CO it corresponds to. So course outcome wise marks distribution. If there are 100 marks, CO1 had 8 marks in this paper, CO2 had 20 marks, CO3 had 54 marks, CO4 had 12 marks, CO5 had 6 marks. So your question paper must have a distribution over different COs. Because this is only one paper. Maybe CO1 and CO2 were given more weightage in the internal test. So you cannot look at only, this is the end semester examination, semester end exam, what we call summative assessment. during the semester, we have internal assessment, which is called formative assessment. So in the formative assessment, we may have only CO1 and CO2, and maybe in another one only CO4 and CO5. All right. So, but you must consider all the different assessment in the course together and make sure that the COs are all are presented to the students for assessment in equal proportion. Something should not be overemphasized. That's like, giving undue weightage to something and omitting or giving low weightage to something. That should not happen. And notice the other diagram that shows Bloom's level, how marks are distributed. For example, level 3 is 46%, level 4 is 36%, and level 2 is 18%. The colors are not very clear. I think level 4 is 18%, level 3 is 46%, level 2 is 36%. So this is important to keep this in mind, that your question paper or your assessment sort of in a reasonable manner has a coverage of Bloom's taxonomy and COs. Okay. So COs help not only to teach and learn, but also in the assessment. Yeah. So in this, I'm going to show the key idea of what are called rubrics. How do we evaluate? Normally in a question paper, we think of an answer key. There's a question, there is a right answer, that's the answer key, and then there are some steps. So we may give part mark for steps. There may be numerical calculation, whatever it is, right? Of course, very simple questions at under remembering level, you just have to check the entire answer and give the marks. Okay, that's it. So such question. So when you have low questions at the low Bloom's level, you have more questions, but each question will carry low marks, like 1 or 2 mark question, but maybe 5, 10 of them, so that the student does not lose out. But when you come to higher level, you may not have so many questions. You may give some choice, either or one of the following 3, something like that. But each of them will be a fairly long question to produce an answer. So you need to give some part marks and so on. However, when you come to projects and things like that, it becomes more complicated. How do you assess a project? So these are called rubrics, scoring rubrics. For example, if you take a subject like, let's say, English language, you might ask the student to write an essay. Let's say essay on some important topic, like essay on tackling climate change, for example. Okay, some general topic like that. So how do you assess the different? Of course, you will give some condition, like the essay should not be more than something like 600 words or something like that, maybe, so that it's not a big book or anything like that. And of course, you want to check for plagiarism and so on. So how do you assess that? So these are called rubrics. So these slides show rubrics for communication, written and oral communication. So this table, the rubrics table, has rows and columns. On the rows will be the type of activity: written communication, presentation with visual aids. So these are the 2. And along the columns will be different levels, different degrees to which the task is satisfactorily met, is well met. Proficient, acceptable, needs to be improved. So for each of that, you describe. For example, needs to be improved, report lacks an overall organization. Reader has to make considerable effort to understand the underlying logic and flow of ideas. There's no smooth flow of ideas. Diagrams are absent or not connected, inconsistent with the text. Grammatical and spelling errors make it difficult for the reader to interpret text in places, and so on. So, for example, now there are good tools to do this. Like if you use a word or even Grammarly and tools like that, you can do a good job. You may encourage students to use those tools also actually. So the idea in these rubrics is that you tell the student in advance, I want an essay from you on this topic by this date, due date to be submitted. And you say this is the way, this is a rubric on which it will be evaluated, so that the student can know the evaluation and accordingly bring up his contribution or his response to the task given to him. So the idea is not to hide the rubrics from the student, but share the rubrics beforehand, a priori, right? In fact, you will see question papers where they'll give you a sample question in the beginning and then give you the part A, sample question, then they give you the question and so on. It's somewhat like that. The rubrics are very important. Similarly, oral presentation. So these rubrics also have to be defined in assessment, depending, especially if you are at the higher Bloom's level, depending on the problem. Because those problems will not admit this is the solution, this is the correct solution, this is not correct, it will not accept. Maybe a solution will be partial. It may not have considered all factors, but what factors does consider it may be satisfactory. So you have to accept that, right? So it's not a binary. And students always come and ask, sir, you gave my friend more marks than me. Why? You can answer if you have the rubrics properly. Right? In fact, they won't even come and ask you. So this shows rubrics for design projects. Purpose of the project, research, or what prior work has been examined, choices, what are the choices the student came up with, and so on. So these are the different criteria, and each of them can be acceptable, proficient, needs to be improved. All right. So this is a rubric with three parameters, and each parameter has 3 levels of performance. You could make it 5 levels, but more levels you make, it's more difficult for you to assess, and it may not serve the purpose. You see, sometimes too much detail is not helpful beyond a certain point. So you have to judiciously prepare this. This is for design projects, and I'll show you 1 or 2 more. So this one again continues: alternative designs, application of engineering principles, final design, interpretation of results, and so on. So these are, you don't have to use it exactly, but this sort of a template from which you can fashion. It's like, custom tailoring your shirt or your clothes and so on. So you can use these templates. They're available, and you can study them, and you can pick what is applicable and so on. One other question I would like to place with you at this point is that what kind of course outcomes will you write for a project? I showed you one right in the beginning in first year. Workshop practice or something, I showed a few. So that's something important because students do different kinds of projects, Some of them will have design, some of them will have troubleshooting, some of them will have analysis, some of them will compare 2 different algorithms or methods of solving something and say which is better for what type of data and things like that, and so on. So you may have to design, depending on the project, certain rubrics specific to that project. In fact, I know some institutions where they have a taxonomy for project. This project is of this type, this type, this type, and so on. Some 4 or 5 types. They also have any other if it doesn't fit into those 5. But for those projects which fit into one of those types, they have the rubrics for it worked out, right? I don't know whether they put it on the web, but I have seen it in that college. This is rubrics for review. Let me show this briefly again. So when you conduct a project review, third review, you're reviewing the project, because project you don't assess only at the end. You need formative assessment. During the project, you need assessment. Otherwise, students will come at the end and show something not up to the mark, and they don't have time to do anything more. So you have to provide mentorship and guidance. All right. So that will involve, this is review 3. Notice there is a group assessment, the individual assessment. So there are rubrics for both GA and IA. All right. For example, if you see the deliver effective presentation, technical, non-technical audience, so that is individual assessment. Present results as a team, that is group assessment as well as individual assessment, and so on. So this might look a little too detailed and complicated, but it is worth doing, because if you do this beforehand, it helps the student to perform better, to do better, and then that will help them in terms of fulfilling the attainment of program outcomes, and that will help them to secure a better future and so on. And you can feel very satisfied that as a teacher, your students are doing very well. Okay, last part. It's 4:11, 4:15. I said I'll finish. So I'm going to finish in another few minutes. This will be a very brief component. There's something about learning styles. I included this material because it's good to be aware of it in terms of pedagogic terms. There are information or a situation, understanding of something can be presented in a variety of ways. It can be presented orally, it can be presented visually, it can be presented kinesthetically, tactile. So these are the 3 broad things. Tactile means touch. See, all learning, all interaction is multimodal. We use all senses that are available to us. We use ear, we hear, we sometimes we speak and interact, we see, and we use our gestures, hands, and so on, body language. So many, especially as a teacher, you use your body language, your eye contact in the class, and so many things. So it's a multimodal experience. A student in a classroom looking at a teacher in a particular class on a subject is actually undergoing a multimodal experience. They have issues of fatigue and so on. The first period, second period, teacher changes, subject changes, all that is there. But it's a multimodal experience. So learning can be visual, or auditory, or it can be tactile. All right. So these are the 3 modes. So what am I going to say about this? Okay. So visual learners learn by sight. Hello?
Yes, sir. Yes, sir.
No, somebody else was talking. I'll just finish in a few minutes, okay? So learning styles, visual learners learn by sight, auditory learners learn by hearing, tactile learners learn by touch. Of course, you may say, what is tactile learning doing in engineering? Well, workshop practice, this tactile learning, texture of materials, all right, and so on. It may not apply for many types, for example, surface finish, okay? Many things, So, for example, this may be much more important, for example, in other professions, like, for example, medical professions. Doctors see X-rays or other images, scan images and so on, and they infer from that and so on. Kinesthetic, for example, in sports, very important. Kinesthetic, tactile learning is very important, and so on. Safety, for example. So I've given a reference here. This gives a questionnaire by using which a person can find out what out of these 3 different modes of learning, which is dominant in him. It's not that we are good at one thing and bad at another thing, but we are very good at something and okay at other things. That's how it is. Everybody can learn in all the different ways. That's not an issue. But it also depends on what material is to be learned. Some material is best learned by. So I have some examples to sort of drive home this point. I'll come to that. Yeah. So here is a simple example. Let's take a second order linear differential equation, simple. So you can have it for a mass spring damper system. X is the displacement, T is time, and F is the force applied. It's a mass spring damper, but can be an RLC circuit. Mathematically, they both come in second order ordinary differential equation. So the differential equation will be P times second derivative plus Q times first derivative plus R equal to some constant. V if it's voltage, F it is force, and so on. So in this case, we have overdamped, underdamped oscillatory systems. If you actually put numerical values and solve it, which you can do easily, you have to create some simple apparatus, not very expensive. You can solve it. Overdamped means that this Q squared minus 4 times P times R, okay, is greater than 0 means it's overdamped. Less than 0 means it's underdamped. Equal to 0 means it's oscillatory. So if it is equal to 0, then you will find that the variable current or displacement will be actually oscillating like a sine wave at some frequency. In fact, this principle is used in creating oscillators in electronics, for example. Now, if it is overdamped, of course, what I'm applying is a constant voltage or a constant force. In that case, the step function. In that case, if it's overdamped, the steady state value, for example, across the capacitance will be V in an RLC circuit. All right. In the case of a mass spring damper system, X, the displacement X will be a constant, F by M, force by mass, because the damping, everything would have settled down. Okay. So, and of course, you also have another case which I have not shown here called critically damped. So overdamped, it reaches a steady value very slowly. Oscillatory doesn't reach the steady state value, it keeps oscillating. Underdamped means it will oscillate but eventually settle down. Okay, some waviness will be there. Critical damp, so in an overdamped system, there is no overshoot. In an underdamped system, there will be overshoot, but it will settle down. In an oscillatory, it will keep oscillating. There's something called critical damping where the overshoot will be just minimal, and that is the system. It depends on the proper choice of values for PQ and R and so on. And that critically damped system will be the fastest to reach the steady state. This is very important in many applications. For example, in chemical engineering, in PID controllers, in many applications, very important, right? We all want, for example, in an automobile, if I want to apply the brake, you would like would you like it to be overdamped, underdamped, oscillatory, or critically damped? Critically damped may be okay, but then the actual stopping will happen with a slight overshoot. Not exactly when you design it to, when you are intended to stop. It will overshoot a little bit, but then come back and stop, okay? All right. So it may not always be acceptable, but again, in critical damping, how much is the overshoot is another question. The point I'm coming to is that all this symbolically never gets in the mind. It gets only visually. If we show this visually, which I'm not going to show here, but I leave it as an exercise for you. If we show it visually, then the student gets it for life, for good. He'll remember it forever, especially if you draw good diagrams or if you show it with an interesting PowerPoint or if you show it with an interesting short video, all right? Which I have not done in this case, but I'm sure you can try it out. So this is the kind of thing I mentioned. Depending on what you're trying to convey, different representations of conveying it make it more easily reached in the cognitive level of the student. All right. So communication is not what is given, but it is what is received. Communication is what is received, not what is given. You may give a lot of stuff on the board, but what is received is important. So therefore, I strongly recommend that you use visual approaches for in as many situations as possible. In fact, You should encourage students also when they make presentations to visually present results. Maybe they can use, remember I showed you that question paper with Bloom's taxonomy distribution and CO distribution. I used a histogram and a pie chart for that. You can use, or you can use diagrams and things like that. So, as they say, a picture is worth 1,000 words. So that's the point I want to make with respect to types of learning. Now, I think I have one last slide on NEP. I'll briefly mention that. Yeah, this is my last slide. Okay, there are many suggestions in NEP, New Education Policy 2020. It's 3 years now. They provide for multiple entry, multiple exit. They provide for students to leave a program, do something, come back, continue. So the credits can be accumulated with purposeful breaks. Of course, students take sometimes breaks for personal reasons, family reasons, personal reasons, but they can also take it so that their experience becomes sort of blended with some industry exposure and so on. So a student could go and spend 6 months or 1 year in industry, not necessarily earn all of it for credit. Some of it may be earned for curricular credits, but not all of it. Come back and continue and fulfill the remaining credits. Or sometimes students may move from one. See, earlier it used to be migration certificate from universities. Sometimes students may move from one university to another university. Now, many institutions are coming up with MOUs with other industries or other institutions for twinning programs and so on. Student can do something here, something in another place, and together properly combined, they can make a degree of some sort. So that will provide for multiple entry, multiple exit. And there is a system being created by government called APAR, Automated Permanent Academic Account Registry. I don't know how many of you know about it, but you can Google this word and go and look at it. Multidisciplinary curriculum. See, whenever we think of a program, we think we are preparing this person for electrical engineering. But he might jolly well do quite a bit of electrical engineering, but in a mechanical engineering oriented industry, for example. Many medical devices have substantial amount of mechanical as well as electrical engineering. Prosthetic devices, for example, to allow people to make use of, to sort of handle challenges for themselves, right? And so on. So what do we prepare to? So what has happened now is that we have minor courses. For example, student mechanical engineering can do a minor in, for example, maybe in computer, some part of computer related field, some aspect of computer science, let us say, and so on. Or a student of mechanical automobile engineering may do some part of robotics. If there's a robotics and automation program in the college, they might offer a minor program. Minor has something about 18 credit requirements in addition to the basic about 160 credits for the 4-year degree. So additional workload will be there. Okay. Then we also introduced Indian knowledge systems, human values. That's recommended by NEP. These are introduced as mandatory courses. So the curriculum gets a little bit overloaded, but it has to be accommodated within the total 160, but sometimes it goes up to 165 and so on. Credit for MOOC courses, then minor majors. So these are some recommendations in NEP which are already finding a place in the curriculum, right? I'm sure at Haldia also you probably have introduced some of these things, or you will be introducing them in due course. Basically, give more choice to the student. Out of this, the multidisciplinary curriculum is the most important. Even for a normal curriculum, earlier the categories used to be common core, engineering core, professional or discipline core, discipline electives, open elective, project. These are the main components, right? Minor is additional. Only it may not be taken by all students. It may be taken only by a few students because they have to do additional credits and so on. But the basic degree itself, discipline itself, will have common engineering core, or including practice. Then it will have professional or discipline core. It will have discipline electives, professional electives. It will have open electives. It will have project. Now, in addition, you introduce a category called multidisciplinary course. In other words, and the total remains the same. So where does this multidisciplinary come? It has to come out of probably the professional electives to some degree, right? So if the professional degree earlier was, let us say, something like about 18 credits, 6 courses or something like that, equivalent of 5 or 6 courses in the 160 credit curriculum. Now you might make it something like 12 or 14, something like that, or 12, and say release 6 for multidisciplinary. The multidisciplinary will be courses of other branches. All right. So, in other words, you're making the electives more purposeful instead of making an elective as a. It's like you go to a buffet, you have several things, but you are not going to pick things at random and combine and eat. You have to pick them in some meaningful way to form a proper sequence that you can eat and digest as for nutritional purpose and so on. Similarly, the discipline curriculum and open electives, discipline elective and open elective may be refashioned to some extent to offer multidisciplinary courses. Sometimes the multidisciplinary aspect may also be embedded within the curriculum of the discipline core itself. For example, I might introduce for automobile engineers a course on electric vehicles in the curriculum itself. So that makes it multidisciplinary in nature. So multidisciplinary need not be thought of only as separate courses. That's one possibility. It's also possible to redesign some of the curriculum and the courses in the curriculum, or particularly the component on discipline core or discipline elective to address multidisciplinary nature. So these are some of the interesting aspects of NEP. It's a vast subject. I'm not going to go into all of it. And I think with this, I'll stop. It's 4:27. I exceeded my time. I now will welcome questions and so on. And one last slide I'll show you.
Thank you, sir,
Thank you very much. Thank you.
for your valuable speech. Now, sir, some questions come through Gmeet and YouTube. One Professor Dr. Vinit Kumar Singh asked that is COs is different for all subject as well as year of engineering?
He's asking about POs or COs. Can you please repeat?
So is COs course
COs.
outcome? Yes.
Yeah. Course outcome depends on the course. See, I didn't talk in this how you connect course outcomes to program outcomes. Program outcomes look generic, but if you read carefully in the program outcome, particularly the first 5, there will be discipline knowledge in that. Based on discipline. So you solve a problem, you analyze a problem, you design solution, you use tools and so on to solve complex problems, and that discipline knowledge will be there. Okay. So the POs are connected to the discipline, even though they read in a generic way. So when you design the courses, the course outcomes have to be connected to the program outcome. That is done by, I think, what your dean mentioned in his brief talk, by developing a CO-PO matrix, sometimes called articulation matrix. I assume you have done it because you have got accreditation, at least for your computer science programs. You would have done it, but there's also some scope to do it better and improve. I have not touched upon it here. Okay, so there are some better ways of doing those things. I don't know how you have done it. It will be there in your SAR. But to answer the question very specifically, COs have to be connected to POs through a CO-PO matrix. So COs cannot be independently designed. So what do we have a course? We have a course title, course number, course syllabus, study materials, assessment method. Sometimes assessment method can be slightly different for different courses. Plus we may have where this course is there in the overall curriculum, which category it is. Is it a discipline core? Is it an engineering core, common core, or is it a multidisciplinary course, or is it a discipline core, or is it discipline elective? Is it an open elective? So you have to have that picture of where this course belongs into the curriculum. So all this is important. Yeah.
Okay, sir. The next question comes, that is, how do we connect POs to teaching learning assessment, and what is the role of performance indicators?
A good question. I sort of let me go back.
Yes, sir.
I'm online. 1 minute. I'm just okay. I think are you seeing any slide there? I'll stop sharing. Okay. I don't need that. Okay. So performance indicator I skirted, but if you look to the reference I gave you two references first, and later I gave you a reference on learning styles. If you look through the first reference, which is an AICT handbook on examination reforms, you will find that performance indicators are mentioned there. The idea is that going from course outcomes to program outcome is a big jump. So to connect course outcome to program outcome, you connect course outcome to performance indicator, and performance indicators can be more conveniently or more meaningfully connected with program outcomes. So that is where the PA comes. For lack of time, I did not mention it. I hope the other speakers in the FDP sessions will mention that. Okay. But the performance indicators are described in full. Also, some of it is there in my slides, not very little, about 4 or 5 slides, which I omitted showing during the presentation. So you can go through it offline. Okay. The idea is that course outcome to program outcome is too big a jump. So you go from course outcome to two, three performance indicators, which will be the basis to assess those course outcomes by the student in assessment. And then performance indicators are mapped to program outcomes. Yeah.
Okay, sir. The next question comes, that how can we the misalignment between the course and program level targets be addressed?
Please repeat the question, madam, a little bit.
How can the different misalignment between the course and program level targets be addressed?
Okay. Okay. So this is about targets. I think the question is about targets. So targets are, I think you're talking about the OBE system detail in some detail. The targets are they have to be set by you. In other words, the idea in setting a target is, suppose at the end of a course, you assess how well the course outcomes have been achieved by the student. You should be very careful. This is nothing to do with the student performance directly. Of course, it is connected to how students have performed, but not individual students. The idea here is that as a class, as a whole, in aggregate, in totality, how well have students performed with respect to, say, the 5 course outcomes. Maybe they have done very well in course outcome 1 and 3, not done so well in course outcome 2, and course outcome 4 somewhere in between, and so on. So the advantage of this kind of a approach is that I can the next offering of the course, I can improve upon my teaching strategy and the learning strategy and the assessment strategy to get better outcomes for those COs. That is the idea. So use the CO assessment. Very simply, you can think of the CO assessment as the entire class's grade point average for that particular course outcome, not for the entire course. Because an individual student may do very well in two or three course outcomes, but not do that well in one or two course outcomes, but still pass and get the credits. We are not expecting every student do everything perfectly. That is not the goal. As many students as possible should be able to achieve a good level, not necessarily the best level, a good level with respect to as many COs as possible. That is the objective. So this is why you're measuring. So the target setting should be such that if you set the target very high, you will achieve very you will conclude that your students have achievement level for course outcomes is very low. If you set the target very low, you will conclude that students have achieved course outcomes to a very high level. Both are not correct. You must do it very judiciously. So the best method to do it is through perturbation. You select 2-3 different targets for course outcome and see. All right. This is done. This is done through what is called as Standard analysis. Standard 9 analysis. Normally these things are taught in a educational pedagogy course, but we don't learn it. None of us go through a pedagogy course per se, but they are available online as well as some colleges. For example, many places have a college of education. Many universities have a college of education. There they will do these courses: curriculum assessment, curriculum benchmarking, curriculum analysis, then pedagogy. These things will be part of a college of education. So in pedagogy, uh, 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 you select this outcome attainment in such a way that you have to do some perturbation. So the standard analysis will tell you, for example, suppose, let's say, to keep my description simple, suppose I have 5 questions, each is 1 CO. Let's take that kind of a data model. Okay, data model. Okay, so 5 questions and 5 COs, and that is a course, right? Suppose I find the standard analysis will say how many students did well in first question, CO1 question. Suppose it's 90%. Then I may set a target which is a little bit stiff for that, right? Suppose I find that question 4, students, very few students have been able to do it well, all right? Out of class of 60, let's say only 15 people were able to do it. Rest of them got maybe some part marks, but not very satisfactory. Let's say less than half the marks or something like that. So I would like to use a lower threshold for that, but still, so the idea is to spot improvement for each CO. All right. So you have to look at it not as a blind method, but as a tool, all right, and use a tool judiciously, so that you can infer which COs need to be focused to the class. Maybe the approach could be that if in one CO students are weak, maybe you use different study material, maybe you'll give more problems, or maybe you'll present the results in a different mode, like maybe visual or a video, something like that, right? So this is a kind of analysis for COs. Now with POs, you can do the CO analysis even during the course, not necessarily at the end of the course, because if you do it at the end of the course, it will benefit only the next batch of students who come to that course. But if you do it during the course, you can do some mid-course corrections. That's called partial CO attainment, because the course is not complete. So suppose I have done only, let's say, internal test. I've looked at only 2 COs, CO1 and CO2. Let's say I had some 8-9 questions, some 4 for CO1 and 4 for CO2. I find out which of these questions many students got it, which of the students many students missed, and so on. Okay, number wise I see. If many students have missed 3rd question in CO1, I know that something in that question is not being adequately reached, adequately supported for learning by students by me, right? So you have to do this analysis. So in other words, the tests are not only to assess students, it's also to assess your teaching. The tests tell you how you can teach better or what you should focus on to reach your material. So, as I said earlier, communication is what is received, not what is given. All right. So, this is the answer. It's a long answer, but this is the answer. So, you must look at the thresholds as parameters that you must do some perturbation and by trial and error fix it. There's no absolute way of fixing it. Okay? This is true of many other things, you see. For example, you take blood pressure. Earlier, they used to say, 110 by 80 is good or 110 by 70. But today, they're saying 130 by 80 is also good. All right. So, there's a judgmental effect required, no? So, you have to learn, and sometimes you may want to do it as a group, not necessarily as a single teacher for a course. In some colleges, the same subject is taught to many sections of students by different teachers. I don't know about Haldia Institute of Technology. If you have that, there are many teachers. Sometimes the assessment may be common also. Even though many teachers are teaching, even if you're autonomous, you may not leave it completely to the teacher. You might use certain common assessments, for example, for internal tests as well as for semester end examination. So they can compare the results, and you may find that different sections come out with different performance levels for COs, individual COs. All right. So these are the things to be studied. Yes, madam. I'm through with
Thank
that
you, sir.
response.
Yes.
Okay.
Thank you. Sir, one more questions.
Yeah.
Yes, sir. From my side, students from different states are present. How should local language be implemented, sir, as per NEP 2020?
Very good question. Very good question. Um, do you have the medium of instruction as local language, or do you have medium of instruction English, but you want to help students by supporting them in local language? I want to understand the question. Are you having engineering programs or engineering degree programs in other than English medium language, or you want to support students? Medium is English only, but you want to support students by using local language. What is your exact question?
Sir, suppose West Bengal mother tongue, maximum mother tongue is Bengali. So
Yeah,
different state like Assam, like Assamia. So
yeah.
so how should local language be implemented?
Okay. It's a very tough question. I myself know only about 3 or 4 languages. So I've helped some institutions in coping with students who know only Malayalam or Tamil, for example. What we do is that every subject, every course you're teaching has some technical words in it. Technical words. Sometimes these technical words are not very rigorous or precise, but they have to be understood in a clear fashion. I'll give you an example. For example, cloud computing. You may not find a very accurate, exact definition of what is cloud computing, right? But at the same time, it has to be clearly understood. So, what I suggest is you take that kind of technical words which are very important for that course, maybe about 8, 10 of them, or even 20, 25 of them, and for each of these technical words which is important in that course as part of that CO and so on, you provide uh, maybe a short explanation of about one para, at best something like a Wikipedia page, if at all. If at all, Wikipedia page also can be sometimes long, and they contain further references. So I'm not suggesting that as a standard. You can take a Wikipedia page, make a local copy, and edit it. Make it simple. So do this for every technical word which is important for the course. And if these technical words also use some technical words of earlier courses, include that and provide that as a guide to the student at the beginning of the course. So after attending a class in whatever medium, English, Bengali, whatever it is, the student can go and refer to that. It will be a very useful aid, because most students are not able to grasp something mainly because they have not grasped the technical words properly. For example, I have taught students from other countries in other places. I have taught students from Africa, I have taught students from Vietnam, and so on. And of course, all the teaching I did was in English. I've taught students in Germany, for example. All these students, the medium was English, but the students in my class were not that good at English. Right? Sometimes they used to struggle. Of course, for German students, I took the German equivalent of technical words. I took the help of some other faculty in that place. I think it was Karlsruhe and Darmstadt, some places like that. And I prepared this dictionary beforehand. In fact, other teachers also started following it after that. That really helps, because once the technical words are clearly grasped and understood by a student, many other things automatically follow from that. This is the best that one can do, you know. It will take a long time to develop full textbooks, full equivalents, and it's also a big question. Should we replace every English word with an equivalent word in another language? Sometimes we do that, but those words are, uh, for example, uh, many other languages use the English word as it is, you know. English also uses some of the Indian words as it is, for example.
Yes, sir.
Yeah. So I think, you know, vocabulary is the most important in a language. And the vocabulary, when it comes to technical education, is a technical jargon, technical words. Common words also you can probably prepare a dictionary and give to students. There are many available. For example, I know Hindi, Tamil, Tamil, Hindi, similarly. And nowadays, these dictionaries are also available on the mobile. So you don't have to have fat books with you. You can just go into the mobile and see. And there are also now softwares available which will give you a page of information in one language rendered in any other language. And some of these software are available in real time. Uh, I saw a demonstration of that in Delhi. It is being it is prepared with the support from Ministry of Electronics, Information Technology, Communications and Information Technology, MeitY. This software in real time, like in Parliament, it will translate what is spoken into another language. But right now, the version that I saw is only for textual display. What is spoken in one language is displayed as a text in another language, but apparently an audio version is also available. So these things also can be used. If you talk in Bengali, you have to see how much that software will be, how good it is. Is it, most of these translation software from one language to another, they might have a reliability of about 85%, 90%, may be good, may not be good. I don't know. You have to evaluate it. But if it is reasonably good, then you can use it for student to listen to what you are talking in another language in the class. This does not require extensive equipment, but it requires a computer, because a computer to capture what you are speaking in one language and convert it to text and map it to another language and convert it to spoken language on the other laptop. Of course, we'll use earphones and so on. The student will use earphones, so he's hearing it in a different language. These technologies are also available. So I think this is a problem which may see some improvement in the next some years, 4 or 5 years, significant improvement in terms of technology aids. So that the teacher speaks in one language, but the student might listen to it in a different language. Possible. Today it may sound science fiction, but it is not science fiction, believe me. I think we'll begin to see some of this available. For example, you're already seeing it in mobile. You can send SMS, WhatsApp, everything in many different languages, right?
Yes, sir.
Yeah, okay. So don't look at this multilingual requirement as a tough problem. It's a difficult problem, but it's a problem that is getting progressively solved better and better. Thank you.
Thank you, sir.
Sir, one last question comes from Professor Indrani Sharkar. That is the online programs in MTech, MBA, MCA like professional courses offered by IITs and other government and private institutions are at par with regular courses.
Uh, okay, you're asking for some benchmarking actually. See, the success of a course, I think it's not. I'll change the question a little bit. Hopefully, it will still be relevant to what was asked by the professor. You see, how much is what is the value added to a student at the end of the course? That is what counts finally. Okay, before the course, the student is at some level uh, in his progression in the overall curriculum. After the course, he is at a slightly different position. So if you look at the curriculum in a plane, one axis as time, another axis as the capability of the student in terms of moving towards program outcomes, let us say, for example. So in this, each course, the student comes to the course at some point in this two-dimensional space, and after the course, he will move to a different point in the two-dimensional space. Because after this course, the time would have gone, one more semester has gone, but he might have progressed in some way. There are many program outcomes. There are 12. Okay, so if you imagine in that space, the value added that we are referring to, and value added completely depends on both the teacher and the taught, not only on the teacher. Depends both on the teacher and the taught. And the value addition is how serious or how well motivated the student is and how motivating the teacher is. Okay, so this is all that matters finally. It's like, I'll give you a simple story from attributed to Ramakrishna Paramahamsa. He had a disciple with him. I mean, he had a person to help him every day-to-day life. And this person asked Swami, sir, you are a very revered person. Everybody is coming to you for great spiritual knowledge. Why don't you give me some of that? So Ramakrishna Paramhansa didn't know what to tell this fellow. He's like, a manual helping person. So he told him, you take a kamandal or a tumbler, some glass, and go and put it in the Hooghly River while you take bath. Come back and show me. So we went and kept the glass with him while taking bath. When he got out, there's nothing in the glass actually. The water was so forceful. So we went and showed it. So Swami said, repeat this. So several days it happened, the glass was empty. Then the Swamiji told him one day, go and don't take bath in Hooghly, or you take bath, but after that go and there's a tap on the bank of the Hooghly near the temple. So you go and put the glass under the tap where the water will be coming only drop by drop. You'll be patiently holding. Come back. So this fellow went and held the glass. After some 4 or 5 minutes, came back. There was some water in it, not full, but little bit. So the Ramakrishna sage told him, go and stay for a longer time. So next day he stood for 10-15 minutes, came back, more water was there. Like that he went on. After about 20 days, when he was patient enough, the glass was full. So what is received depends on the receiver and the giver, both. That is the important thing to remember. So my humble submission to you is that you can learn from the study material, the exam questions in NPTEL and all that. As a teacher, you may want to do an NPTEL course in the subject of interest so that you can see how as a student, you experience that course. But then you must connect it with the students in front of you in the class. You cannot simply repeat the same course because as a teacher in HIT, as a teacher of a course in students in front of you, you are not a teacher in IIT, and the students in your class are not students of IIT. They are different. All right. So keep that in mind. do learn from everything, but adapt it to what you have to deliver for your responsibility and your role. Thank you.
Thank you,
Shall
sir.
we close it? Yeah.
No, sir. One more thing, sir. Thank you. And this is the some token of appreciation from our side. This is the your.
Oh, thank you. Thank you very much. I am delighted. It's signed by the principal, registrar, dean, IQAC coordinator, and program chair, HOD CSC. Thank you very much. Wish you a bright future. All the best to you. I'll be happy to remain connected with you, with HIT, in future occasions, wherever possible, where you think it's appropriate. God bless you. Thank you very much. Namaskar.
Thank you, sir. Sir, please
Namaskar.
turn on, if all of you available, please turn on your camera, capture some photos actually.
Sure.
Yes.
Yeah. I will remove this.
Everyone is possible. Please turn to your camera.
Want me a little bit closer to the camera? Is it
Thank you,
okay?
sir. Thank you, sir.
Thank you. Thank you very much.
Thank you.
Thank you, sir.
If you get feedback about this, please pass it on to me. I would like to listen to your note your feedback and improve. Thank you.
Of course, sir.
Thank you, sir. Definitely, sir.
Thank you, sir.
I'm now leaving the call. Okay.
Yes.
Good night, sir.
Good day. Good day.
Good night, sir.